Today we discuss about step potential. It is one of the application of Schrodinger wave equation. In that article, we discuss quantum mechanical treatment for motion of particles along x-axis across the step potential for E greater than V0 and E less than V0. And then we discuss reflection and transmission coefficients. Here we discuss quantum mechanical treatment for the motion of particle along x-axis across the state potential. Such a state potential is represented here. It is a barrier between the two regions at x equal to 0. It is just like a step. Therefore, the name we call state potential. The potential in the region 1 is 0, while in the region 2, potential V is equal to V0. Mathematical representation of the step potential is given here. V equal to 0 for x less than 0 for region 1 and V equal to V0 for x greater than 0 for the region 2. As the particles are moving along positive x direction, we are considering a beam of particle or the number of particles moving along positive x direction per unit time per unit area, that is incident particle flux. Such a particle flux has total energy E equal to Ek plus V0, that is Ek is equal to E minus V0. Here for the region 1, potential energy V is 0, therefore the total energy is only kinetic energy. While in the region 2, when the particle enter into the region 2, the kinetic energy is reduces, and that is E minus V0. Hence we study the quantum mechanical treatment for the two different cases, E greater than V0 and E less than V0. For E greater than V0, there is partial transmission probability and partial reflection probability. That is, total probability is always equal to 1. But the same case when we study with classical treatment, then there is perfect transmission and no reflection for E greater than V0. But quantum treatment, it shows transmission probability reaches to us maximum, while reflection probability reaches to us minimum, that is R tends to 0, that is partial transmission and partial reflection for E greater than V0. Similarly, for other case, E less than V0, then transmission probability becomes minimum and reflection probability tends towards 1, that is maximum, but total probability is again 1. Such two cases we have to study in detail by using the Schrodinger steady state equation for E greater than V0 and E less than V0 in detail. Firstly, we explain the case E greater than V0, that is total energy is always greater than height of the potential barrier. Then quantum mechanically we prove that there is partial transmission, that is T tends towards 1, and partial reflection R tends towards 0 for the case E greater than V0. Hence we use Schrodinger's steady state equation. The general equation is given here. D square psi of x by dx square plus 2m by h cross square E minus v of x bracketed term multiplied by psi of x equal to 0. Now we apply this equation for region 1 and 2. For region 1, where potential is 0, therefore this equation becomes d square psi 1x by dx square plus 2m by h cross square E psi 1x since v is 0. Where psi 1 is the function for the incident particle in the region 1. If it enter into the region 2, function changes, and that hence the second equation we write for region 2. The equation 1 is d square psi 1 by dx square plus k1 square psi 1, where k1 square is constant. That constant we express in terms of energy, that is 2m by h cross square E. Similarly, for the region 2, x is greater than 0, where potential V equal to V0. Here we substitute V of x by V0 and write the same equation, but function for region 2 is psi 2, hence d square psi 2 x by dx square plus 2m by h cross square E minus V0 psi 2 x equal to 0. Here 2m by h cross square E minus V0, we write another constant, and that constant is k2 square. Hence d square psi 2 by dx square plus k2 square psi 1 equal to 0. Equation 1 and 2 are second order differential equations in terms of constant k1 and k2. What are the k1? For the equation 1, k1 is square root twice me by h cross square, and k2 is equal to under root twice m e minus v0 by h cross square. Now we solve the equation 1 and 2. Now what is the solution that we discuss here? The general solution of equation 1 and 2 is, for region 1, psi 1x equal to a into exponential ik1x plus b into exponential minus ik1x. Similarly, for region 2nd, that is x greater than 0, psi 2x is equal to c e raised to ik2x plus d e raised to minus ik2x. This is the equation, next equation. In that equation, for region 2, c into e raised to ik2x and d into exponential minus ik2x. In that, only possible term is c into ik2x, that we explain here. Psi 1x is equal to a into e raised to ik1x plus b into exponential minus ik1x. Here, exponential ik1x for the region 1, it represents wave function for incident particle flux. Second term represent in the same region, the particles are reflected at x equal to 0. Therefore, this is the reflected particle flux. But for the region 2, c into exponential ik2x, it represents the transmitted particle flux in the region 2, and these particles are moving in positive x direction. But the second term, d into exponential minus ik2x, no any barrier is beyond x equal to 0. Therefore, no possibility of the reflection of the particle in the region 2. Hence, second term for the region 2 is not possible. Hence, the possible solution for region 2 is only psi 2x is equal to c into exponential ik2x, and this is the next equation number 4. Here, equation 3 and 4, a, b, c are constants. That constants we determine here by using the boundary conditions. Now, we know that at the boundary x equal to 0, the wave function is continuous as well as their derivative is also continuous. Hence, psi 1x for region 1 must be equal to psi 2x for region 2 at the boundary x equal to 0. Therefore, derivative is also continuous, d psi 1 by dx equal to d psi 2 by dx. We apply this condition and find constant a, b, c. From equation 3, the first condition we apply from 3 and 4, psi 1x equal to psi 2x at x equal to 0. If x is 0, exponential 0 is 1. Second term also exponential 1 divided by exponential 0 is again 1. Therefore, psi 1 term on one side is a plus b after putting x equal to 0. On the other side, exponential ik2x, c into exponential ik2x, x is again 0. exponential 0 is 1, hence other side is c. Hence for first condition psi1x equal to psi2x, we get the equation a plus b equal to c. Second condition, d psi1 by dx equal to d psi2 by dx at equals to 0, that we find here. Initially we differentiate psi1 term with respect to x and then put x equal to 0. Similarly psi2x, differentiate it with respect to x and put x equal to 0. We get the resulting terms. Here d psi1 by dx, if we differentiate exponential term, it gives a into exponential ik1x into coefficient of x ik1 plus b into minus ik1 into exponential minus ik1x. We put x equal to 0 again, then only remaining terms we write directly here. ik1 a minus b equal to ik2 c. Similarly psi2 term also differentiate with respect to x. After differentiating, put x equal to 0, exponential term is 1 and remaining term we write ik2 c. This is the equation b. From equation a and b, we find constant. Hence initially we multiply equation a by ik1 and we add in the equation b, we get direct result. That result is twice ik1a equal to I into ik1 plus k2 into c. Since on the other side we have to multiply ik1c, already here is ik2c, hence we take I common, k1 plus k2 into c. I cancel on both sides. Therefore we find c term in terms of a, and it is c is equal to twice k1 divided by k1 plus k2 a. This is the next equation number 5. Similarly, we find another, this c value we put in the equation number 1 and we find another constant a plus b equal to c. What is value of c? Twice k1 divided by k1 plus k2 a. Simplify this, separate b term. Therefore a automatically take on the other side. Here is minus a. We take LCM k1 plus k2 and we take the numerator addition, twice k1 minus k1 minus k2. Therefore simplification term is k1 minus k2 divided by k1 plus k2 into a. This is another constant in terms of again a. Now we know the both constants b and c in terms of a, that is given by the equation 5 and 6. Then we find what is the probability current density. We find one-dimensional probability current density for incident, reflected and transmitted waves. What is the general formula for probability current density? That we firstly note here. Probability current density for one dimension equal to h cross divided by 2mi into bracket psi star dava psi by dava x minus psi dava psi star by dava x. We use probability current density for incident wave, reflected wave and transmitted waves. Therefore the equation becomes J incidence is equal to h cross divided by 2im into bracket psi incidence star dava psi by dava x psi dava x. Here is psi incidence minus psi incidence into dava psi star incidence divided by dava x. Now what is psi incidence? A into exponential ik1x. That is for the region 1. We know that we get the solution. Two terms a and b. First term is a into exponential ik1x. This is the wave function for incident wave. Hence we substitute this term in that equation and simplify. Therefore we write firstly in terms of probability current density for incident wave, that is psi incidence, J incidence is equal to h cross divided by 2mi into bracket psi incidence star dava psi incidence by dava x minus psi incidence delta psi star incidence divided by delta x. Now what is the complex conjugate of the psi star incidence is A into exponential minus I k1x. If we substitute values here, we find directly the result. That result we note in the next, after this next equation. Similarly, we also write the probability current density for reflected wave and transmitted wave. As we know, what is psi reflection? B into exponential minus I k1x, and psi transmission for the region 2 is C into exponential I k2x. Therefore, the probability current density for reflected wave and transmitted wave is given here. J reflection is H cross divided by 2 mi into bracket psi star reflection into delta psi reflection by delta x minus psi reflection into delta psi reflection star by delta x. Similarly, probability current density for transmitted particle flux is equal to H cross divided by 2 mi into psi transmission star into delta psi transmission by delta x minus psi transmission into delta psi star transmission by delta x. Now we put these two terms and their complex conjugate. We find direct results. Here we get the simplified terms for probability current density for incident particle flux, reflected particle flux, and transmitted particle flux. If we substitute psi and their complex conjugate in the related equation, we get the result. J incidence is equal to H cross K1 by M into modulus of A square. J reflection equal to H cross K1 by M into modulus of B square, and J transmission equal to H cross K2 by M into modulus of C square. As we know, probability current density for incident, reflected, and transmitted waves, we find probability of reflection and probability of transmission. Hence, the reflection coefficient we define it as R is equal to the probability current density for reflected particle flux divided by probability current density for incident particle flux. We know that J reflection is H cross K1 by M into modulus of B square, and J incidence is H cross K1 by M into modulus of A square. If we take the ratio of these two equations, we get modulus of B square divided by modulus of A square. Similarly, that value we find from the equation 6, since constant B we find earlier in terms of A, we take the ratio B by A and we get the reflection coefficient R is equal to B by A into B by A. We take the square K1 minus K2 bracket square divided by K1 plus K2 bracket square. This is the equation number 6. Similarly, we find transmission coefficient, and it is defined as J transmission divided by J incidence, and it is K2 into modulus of C square. J incidence is K1 into modulus of A square. Since J transmission is H cross K2 by M into modulus of C square, and J incidence is H cross K1 by M into modulus of A square. H cross M is common for numerator and denominator. It get cancelled, and remaining term is K2 by K1 into modulus of C square divided by modulus of A square. From equation 5, we find earlier one of the constants C in terms of A. We find C by A and put here C by A into C by A. K2 by K1 is kept as it is into C by A. We take the square 4K1 square divided by K1 plus K2 square. If we simplify whole the term, here K1 square is K1, denominator 1 get cancelled, and numerator term is 4K1 K2 divided by k1 plus k2 square. As we find probability of transmission and probability of reflection, or reflection coefficient and transmission coefficient, total probability is always equal to 1. That is t plus r equal to 1. How we get t plus r equal to 1? Substitute t, 4k1 k2 divided by k1 plus k2 bracket square, plus r value is find here, k1 minus k2 bracket square divided by k1 plus k2 bracket square. Simplify these two terms, denominator is same, only we take the numerator addition. 4k1 k2 plus, here k1 minus k2 bracket square expand here, k1 square plus k2 square minus twice k1 k2, and we get simplified term is k1 plus k2 bracket square divided by k1 plus k2 bracket square. Both term is same, it get cancelled and we get 1. Hence for E greater than V0, total probability we find and it is equal to 1. Now we see what is the conclusion we get for E greater than V0. Suppose E is very greater than V0, then K2 tends towards K1. Since K2 is one of the constant for the region 2, K1 is another constant for the region 1. If total energy is very large as compared to height of the potential barrier, then K2 becomes equal to K1. Then what is T? T, find this T coefficient of transmission we find earlier. It is 4k1 k2 divided by k1 plus k2 bracket square. In that, if k2 tends towards k1, denominator is twice k2 bracket square, that is 4 k2 square. Here is k4 k2 square. Numerator denominator is same and we get t tends towards 1. Similarly for r, k1 minus k2 bracket square divided by k1 plus k2 square. If k2 tends towards k1, here this term is bracket square k1 minus k2. This is one of the term. Here is 0. Therefore, we get r tends towards 0. Here is numerator is k1 minus k2. If k2 tends towards k1, this term to be 0 and we get r tends towards 0. But total probability is always equal to 1. What is the quantum result? Quantum mechanically we prove that there is partial transmission and partial reflection. Now what is this probability of transmission? It reaches towards maximum, t tends towards 1, since total energy is very greater than height of the potential barrier. There is a maximum transmission of the particle. But at the same time, is a partial reflection is also possible for the same case, means it is r is not equal to 0, r tends towards 0. Say that here r, classically we prove that t is 1 and r is 0. Here we say that in the region 2, when the particle enter into the region 2, there is some loss of the kinetic energy. If the energy is lost in the region 2, we say that some energy spent in overcoming the potential barrier at x equal to 0. It means there is some probability of finding the particle in the region 2. Due to the wave behavior of the particle, if there is some probability of finding the particle in the region 2, there is a partial reflection, that is r tends towards 0 and t tends towards 1, and that is the proof for the case E greater than V0. Now we see the another case, E less than V0. Now what is transmission and reflection coefficient for E less than V0? That we also find here. The solution of the wave function psi1 for the region 1 is same as the earlier case, and the solution we find earlier, psi1 x is equal to a into exponential I k1 x plus b into exponential minus I k1 x. But for region 2, we choose another constant, alpha square equal to twice m by h cross square v0 minus e, since e is less than v0. Hence, we write v0 minus e, and this is another constant for region 2 alpha square. Therefore, what is the solution for region 2? If we solve this differential equation, d square psi 2 by dx square minus alpha square psi 2 equal to 0. That differential equation has solution. Psi has two solutions. One is e exponential minus alpha x, and other term is exponential plus alpha x. But exponential alpha x plus alpha x is not possible for the region, since as x tends towards infinity, exponential term also tends towards infinity. Hence, this is not possible term. Only possible term is psi 2x is equal to c into exponential minus alpha x. Now we find what is the probability current density for the transmitted particle flux for the region 2. As we know, psi 2x is equal to e into exponential minus alpha x. We use the definition, earlier equation, substitute all the terms. Here is no complex term is here. It is as it is. We get J transmission is 0. Now we find what are the constants ABC using the boundary condition at x equal to 0. Only we find the first term b by a, and it is minus alpha plus ik1 divided by alpha minus ik1. Since psi 1 term is a into e raised to ik1x plus b into e raised to minus ik1x equal to c into e raised to minus alpha x. We solve the equation, we get this equation. Then we find probability current density for reflected. We find the transmission and reflection coefficients. Firstly, we find reflection coefficient, J reflection by J incidence, B by A is known, B star by A star into B by A. Since B by A we find earlier in terms of the complex number, therefore we write these two terms separately. Simplify B by A star into B by A. Numerator denominator cancel and we get 1. What is T? Transmission coefficient, J transmission by J incidence. It is always equal to 0 since J transmission is 0. But total probability is 1. T plus R is equal to 1. Now what it shows here, when E is less than V0, the quantum treatment shows partial transmission and partial reflection. But here, probability of the transmission is minimum and probability of reflection is maximum, that is R tends towards 1. But total probability is 1. But how reflection coefficient tends towards 1 and T tends towards 0, that we discuss here. It seems that if the particle enter into the region 2nd, there is some probability of finding the particle in the region 2. If the particle is found in the region 2, it is represented by the function exponential minus alpha x. Such a phenomena of the particle penetration is called as barrier penetration. Graphically we represent here, this is a step potential. A wave is propagating in forward direction x-axis. If energy is less than V0, initially in the region 1, total energy is equal to kinetic energy since potential energy for the region 1 is 0. As the particle enter into the region 2, its kinetic energy reduces. Means particle is definitely found in the region 2. Such a short tail of a wave which is found in the region 2 is represented by the function exponential minus alpha x. It indicates there is some probability of finding particle in the region 2. That phenomena is known as particle penetration or barrier penetration. And that is the result of the motion of the particle across step potential using the quantum treatment. Thank you.